And why is that in front of that? There we go. Perfect. So all is good, and I think all marks are ready to go. The class average for test 2 was outstanding. Great. I think it was 78% and 78.5. And yeah, I think you guys are doing outstanding. So just keep on trucking, and we've got what, 6 weeks to go? Because I think this is a short half, right? So it's only 6 weeks. So we're gonna be moving and we're gonna be shaking. But you guys are 75% way done pre-health. Congratulations. Like really, and you guys took the initiative to come back to school for whatever reason. That's your own personal choice. And you guys are almost done this. So don't you dare take your foot off the gas. Don't you dare take your foot off the gas. Yeah, that's it. I like it, Jess. That's good. And just keep on trucking. We've got 2 more tests on for physics there, and you can see the tests. Like I don't know. Class averages are really good, and so you just guys just keep on doing whatever it is you're doing, and you're just everything is great. Um, do you guys have any questions for me? If you any emergencies, you can shout it out now, or you can save it there till after. You can email me privately, whatever you guys want to do. It's all good. Hey, Brittany, what's going on?
So for the lab, when you're asking for height of stairs, do you
Hmm.
mean the individual step or
Yeah,
the actual height? Oh, okay.
yeah. Just because um, I hope you guys are enjoying this lab. It might uh, you know uh, I don't know. I thought it would be kind of fun. I hope it's not stressing you guys out too much. But yeah. The when I'm asking you there for the measurement of the step, it's the vertical distance. I'm not interested in the horizontal where you actually put your foot. I'm just interested in kind of the back. So you want to measure the back of the step, the height of that step, and then go to the next step, measure that height, and so that eventually, you're going to get a I don't know a height of 6 meters or 5 meters or however. So then that'll be your total height of the stairs. Talk to me, Brittany.
Okay, yeah. So I was wondering if I needed to measure the flight of stairs or the step, but yeah, I guess just if each step is the same size, just multiply that by how many steps and I'll get the height.
Yeah. Be careful. My first year back from the Middle East there, from traveling there, I was doing this course, and the I assumed like we would have all the students in lab, and then for this particular lab, I send them all out into M building, and I have 30 students running around M building, trying to find stairs, right? And as it turns out, generally the steps are not the same height. So just be careful with that. We like to think that the steps are the same height, but sometimes, man, they're off by like 2 or 3 centimeters, like one upon the other. So have a look at it. It's more about just kind of practice and getting you guys out there and thinking about getting you guys out into the world, because we can't meet. I can't bring you into the classroom. So you know what? Darn it, the world is going to be your classroom. So hopefully sure, you can resubmit. It's if there's any issues, let me know there, Joanna. But that's what I'm looking for, and it's all just the most interesting graph is the last graph, and I don't know if I think I did mention it there 2 weeks ago. The I had a group, and there was a really big guy in there. He must have been maybe 6'3", massive. And in the same group was a person of shorter stature. That's all I need to say. And the of course, the bigger person will have more power. But then you in the last graph there, I think it's power divided by mass. All right, which means the amount of power per kilogram. All right, the amount of power produced per kilogram of U. And as it turns out, the person of smaller stature actually had more power per kg than the bigger one. And it's just kind of interesting. And I would rather have you guys in class because then I can, but you can't. So have some fun with it and let me know if you guys are having any issues. But good question. What else we got? Anything else? Emergencies? Be quiet, Ian. Let's go. Done. All right. So I am recording this and I will put this there to YouTube. Okay. And tomorrow we have week 8. So I could have posted a video, but I would rather have you guys here because you guys have questions. And since this is going to be recorded anyway, then your questions there are probably the same as the other people who are going to watch the video. So there we go. So this one isn't too bad. All right, let's go. The physics of matter. All right, and I'm going to move this down. Please tell me if you guys can't see anything. It's been a week of just marking and mayhem, and my kids might pop in and say hello, so it is what it is. Matter, phases, forms, and forces. Matter is anything that has mass and occupies space. All right? It can be classified into 4 categories. There are basically 4 states of matter. That's what this is saying. There's solids, liquids, gases, and maybe you didn't know about this one, plasma. And solids, these are rigid. They have their own shape. All right, these are, a table, a chair, a tooth, a banana. These are solids, right? Liquid takes the shape of its container, okay? And like what happens here is the easiest example is just a block of ice, right, at minus 20 degrees. And the atoms, they can't move, right, because it's a solid, so they vibrate. All right? So even at minus 20, it's very cold. Compared to absolute zero, it has a huge amount of energy, so those atoms are vibrating. And then if you add more heat, all right, then what happens, they start to vibrate more, and then you get the popcorn effect. Pachoom, pachoom. These water molecules that were locked up with the ice, now they break off like popcorn, literally. And then you keep adding more heat, more popcorn, and eventually you get liquid water. They're freer, but not completely free, because water has has a huge form of attraction, right? Because it's a polar molecule. And so now we start heating up the liquid water, okay, and it's moving around and getting faster and faster and faster. And then when it gets to 100 degrees Celsius, pachoom, you get more popcorn. And instead of going from a solid to liquid, now we're going from liquid to a solid. Whoa. Let's do that again. Instead of going from a solid to a liquid, we're going from a liquid to a gas. All right? And you get the same popcorn effect. And now, once all of the liquid water has been evaporated, boiled off, right, and all the water molecules are steam and floating around, that's where we get into a gas. Readily conforms to the shape of the container. It can be compressed. Okay, you'll remember there from your chemistry. All right. And so now you have this gas. You see, we've added heat to the ice to make liquid. We've added heat to the liquid to make a gas. I can keep adding heat to that gas. And I mean, now we're up to 5,000 degrees Celsius. Now we're just kind of way off the charts. Something weird happens when you get up into that area. This is like the whole the chemistry there behind the sun, right? You get plasma, and and if we go back to a solid piece of ice and progress, you've got a molecule of water as ice. You'll have a molecule of water as liquid water, and then you'll have a molecule of water as steam. It's all the same. Water, water, water. But once you get up into plasma, 5,000 degrees Celsius and all that, now there's so much energy. There's no more popcorn effect. There's no other place to go. So what happens is the electrons and the nucleus, they just kind of get ripped from each other. So you have this primordial soup of electrons and nuclei, protons, neutrons. It's just this mashed potatoes of just mess of electrons and nuclei floating all around. And that's basically what plasma is. Okay, you've blown the electron cloud right off of the nucleus. All right, so that's what plasma. Plasma is all the properties of a gas but conduct electricity. All right, interact strongly with magnetic fields and typically exists at higher temperatures. Okay, so there's 4 states of matter. I'm not looking at my comments section because I want you guys to see what's going on. If there's any issues, just give me a shout out, and we'll answer any questions, whatever you guys need. Many substances in our world do not fit easily into one state of matter. All right, like you can pour sugar. When you pour things, it generally is like a liquid, right? But sugar isn't a liquid. Here we've got syrup or some type of sticky substance. All right, kind of acts like a semi-solid sometimes. Many substances are composites of matter in 2 different states of matter. Look at us. We're solid, liquid, gas as well. Even if you look at styrofoam, it's got air in it. Coca-Cola is a solution with all these different solids dissolved in it as well as carbon dioxide. The matter phase of matter can change with temperature. Of course it can. Even if you look at CO2, if you dry ice, like I don't know if you guys ever been to a rock concert, they just have big blocks of frozen carbon dioxide. And what happens is it sublimates. It doesn't go into a liquid. It goes immediately from a solid to a gas. It's called sublimation. Okay. What else we got? The chemical elements represent the simplest and purest forms of everyday matter. Okay, periodic table. This is going to be basic review. I'm sure you guys are familiar with the composite of what atoms are. The 114 different atoms. I think they've added a couple more actually since I made this PowerPoint there, but that's fine, you know. And it's interesting to note that only about 90% of the elements exist naturally on Earth. Okay, like plutonium is not natural. Okay, it's human-made and highly reactive. But the uranium is the last, uranium-238, it's the last naturally made element. Nucleus is composed of protons and neutrons. You guys are aware of that. Electrons there, okay. They have a negative charge, which opposes the proton's positive charge. Neutrons have no charge. They just add mass to the nucleus. Okay, here we go. You guys have any issues there with this, please let me know. Okay, I'm just kind of moving quickly on this stuff here. Solids, liquids, and gases. The solids there, the attractive force between the molecules are very strong, and the molecules are the atoms there, they just vibrate, they can't move. Liquids, the molecules are bound together, but they're not as tightly. That's why water, the molecules there will flow, but there's they are highly attracted there to each other because water is a polar molecule, and you can take a shoestring to a faucet. Sorry, I'm trying to do this in front of my camera. Take a shoestring there to the faucet, and you just turn the water on a little bit, so it's just kind of a trickle, and you get your shoestring out, and the water will actually, instead of falling down due to gravity, it'll actually snake along the shoestring. It's kind of a good little thing there if you have kids to get them into science. Gases, attractive force between the molecules are very weak. Okay, so gases, They're just they really don't. For all intents and purposes, gas molecules don't really have any attractive qualities to them. Okay, and they're only in contact with each other when they collide. What do we got here? Solids. Solids that do not have a regular crystalline shape are called amorphous. And you see, like, this is a typical ionic solid. Sodium chloride, salts. Sodium chloride, sodium chloride, sodium chloride, sodium chloride. It's all connected to each other. All right. Let's have a look here. Carbon. This is a very strange one, and I have to say, oh, my phone's over there charging. Please try. I know everyone likes to get the new, the next iPhone, or they need to update your phone. And you know what, go for it if that's your thing. But I'm just giving you guys a bit of a heads up. Try and hold off on getting that new phone, because I think that things are going to change very, 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 very quickly in the next coming while. And it's because of this human-made, non-natural carbon compound called graphene. Graphene, graphene. And you see, carbon is a very strange one. And for the chemistry, everyone will be starting their organic chemistry there this week. Okay, weeks 1 to 7 of the chemistry is math-based calculator. Now you can throw your calculator away, but don't do it because you're going to need it from my course, physics. But for the chemistry, you really shouldn't need a calculator anymore. It's all organic chemistry, and it's the chemistry of carbon. And carbon can be in many different forms. Like you have graphite that we use there for tennis rackets or pencils. Diamonds. It's just carbon in a different geometric form. All right? And diamond's the strongest substance that we know of. Well, not anymore. Have a look at graphene. It's a new way of looking at. It's going to change everything. I don't know if you guys heard there a couple years ago, a company there in Asia came out with a flexi phone. I think it was only black and white at the time, but yeah, it was a phone there that you can bend and flex and all. You think, how can you do that? It's because of graphene, this newly discovered, well, I guess it's over 10 years old now, maybe 12 years old. 2 Russian scientists there at Manchester University created it. And the amazing thing about it is the strongest substance known to humankind was diamond. This stuff here, it's just carbon, and if you had a spider web of it hanging down from the ceiling, it could hold up a Ford F-150 truck. A spider web. That's how strong this stuff is. So diamond, gone as far as the strongest substance. The most electrically conducive substance is gold. Number 2 is silver. Number 3 is copper. And if you see them there in the periodic table, okay, they're called the money metals, and they're all in the same column in the transition metals. There's a reason for that, because they are related. Gold is the most electrically conducive, very expensive. Silver, number 2, very expensive. Copper, number 3, not so expensive. That's why we use copper wiring in all of our wiring, right? But graphene is the most electrically conducive substance that we know of, as far as I know. And the amazing thing there with graphene is that you can make it into sheets, 1 atom thick. So it's just a sheet of carbon atoms that you can fold into a cylinder. Now this is atomic level, right? Okay, 10 to the minus 8 meters. And basically now you have a wire that is atoms wide instead of, a normal copper wire, which is 3 millimeters wide. So now you can get the same electrically conducive wire at the atomic level. So now, the way I see it is you can get a Ferrari engine into the size of a stapler. Interesting. So graphene, it's it's going to change everything. It's going to change everything. Do some research on it. Maybe write a paper on it there sometime. Good stuff. Liquids. Okay. There is still some attractive force. Okay. But they're more free. Gases, really there isn't any. Okay. And you see that? Gas atoms have a relatively high speed. 1,000 miles an hour. So that's 1,600 kilometers per hour. You're getting hit with oxygen atoms moving at 1,600 kilometers an hour. Ouch. Density, you guys are familiar with this one. Okay. Density is just mass over volume, and it can be measured in grams per cubic centimeter or kilograms there per meters cubed. Okay. Measure density by finding the mass of a sample and dividing it by the volume of the sample. The actual size of the sample is irrelevant. If you use a sample with twice the volume, you should have twice the mass. Okay? So density is this relationship that compares the amount of atoms, grams, divided by or per volume, milliliters or liters. Okay, and that's density, is the amount of atoms in a given volume. All right. The measuring density by finding the mass, the actual size, that's good. Let's move on. Here's an example here. Pretty basic example. What is the density of a 200 kilogram block of material that measures 0.4 meters by 0.6 meters by 0.2 meters? Okay. So there's your mass, 200 kg. Here I've got this information here. Okay. How do I figure out volume? Volume is equal to length times width times height. Okay. I don't think I put that in the formula sheet, but you should know that anyway. Okay. And this is how you do it. So there's your density. And density here is 4,166.66 kilograms per meters cubed. So 1 meter cubed of this substance, it will weigh 4,166 kilograms. Here's another one. A large banquet room measures 12 meters wide by 6 meters long and 8 meters high. What is the mass of the air in the room? Okay, if the density of air is 1.29 kilograms per meters cubed. Here, I've given you the density. Okay, I've given you the volume. And what is the mass? Rearrange your formula, plug and play. Okay. What do we got here? Which has the greatest density? 1 kilogram of water or 10 kilograms of water? They both have the same density, because water, 1 kilogram of water, 10 kilograms of water, water has a density of 1. All right. Which has the greatest density? 5 kilograms of lead or 10 kilograms of aluminum? Okay. I think that there's a table in your book there that has different densities of different materials. If you had a piece of ice, and if you had 1 gram of ice and 1 gram of gold, and like you put them into an aquarium, the ice will float, the gold will go right down to the bottom, because gold has more atoms per milliliter in it than ice. All right. So number 3, which has the greatest density? A whole candy bar or half of the same candy bar? What happens to the volume of a loaf of bread that is squeezed? What happens to its mass? What happens to its density? So, what happens to the volume of a loaf of bread if it's squeezed? Well, you're squeezing it, so the volume's going down. What happens to its mass? Well, the mass, that'll remain the same, right? Just because you're squeezing a piece of bread doesn't mean you're changing its mass. And what happens to its density? It increases. Okay? So you can actually alter the density of a loaf of bread just by squeezing it. What do we got here? Mechanical laws of matter, pressure. So whenever a high-speed gas atom impacts an object, whenever you get hit by a gas atom, it imparts a relatively large force. So it is this force that produces a pressure on the container. Like, you blow up a balloon. Why does a balloon increase in size? The balloon doesn't want to increase in size. It wants to sit there on my tabletop. But I'm forcing air inside, and the air is going in, and it's pushing the balloon. Okay? It's exerting a force on the inside of the balloon. Gases are easily compressed because the majority of their volume is empty space. Okay? If you compress it enough, you force the atoms close enough together that you can form a liquid. All right? And like people who use oxygen tanks, people who have COPD or anything like this, any type of respiratory illness, okay? There are companies out there that will deliver oxygen tanks so people can function normally, okay? And what they do is they just take oxygen gas and they just compress it, push the molecules together, and they form a liquid. And therefore now we can put it into a tank and sell it. Propane, barbecue tanks. It's a liquid inside the tank. You release the nozzle, turns into a gas. Coca-Cola cans. The CO2 is in the Coca-Cola. You release it, you release the pressure, all the gas comes out and returns to a gas. Here's a new formula for you. Okay? Pressure. And what this is the force exerted over a unit area. So pressure, like if you think about the wearing sneakers and then wearing high-heeled shoes. Okay? The sneaker is more comfortable per se because the pressure of your foot is spread out over the area of the shoe. But if you look at a high-heeled shoe, you have the same pressure of the foot, but now on, I don't know, what do you call them, a stiletto, the back heel. And that's why there's more pressure. That's why wearing high heels or anything like that will be a little bit more uncomfortable. And the formula for this is pressure is equal to force divided by area. Okay? And force, you've seen that before. You may need a formula or two from previous tests there to play with this formula here. So pressure is measured in units of newtons per meter squared, or what we call the Pascal. Generally, when you watch the Weather Network or something like that, or in some of my chemistry questions there, we don't use the Pascal. We use a kilopascal, kPa, which you've heard of there before, right? Normal atmospheric pressure is 1 atmosphere or 101.3 kPa, kilopascals. But here pressure is just in a pascal, so it's 1/1000th of a kilopascal, okay? And 1 pascal is essentially the pressure of a dollar bill lying on a table. So you put a dollar bill, here I just have a piece of paper, all right? There, it's from an old envelope there that I just ripped off, and you just set that on the table. That's about the amount of pressure of 1 pascal. Okay. Example, why would you rather wear a pair of flats or high heels? And it's the what I was just talking about there, the difference between a pair of sneakers and a pair of high heels. And you have a look here. I've tried to manipulate this so it could kind of be a little bit of a visual representation. But see, here's your same formula. Pressure is equal to force divided by area. Well, if your area is very big, like a sneaker, then it means your denominator is going to be very big. So therefore, your pressure, your answer will be very low. Okay? But then you look at the high heel example where the area is very small. The back heel stiletto. And if the denominator is very small, then that means there that your answer is going to be very big. So that's why the pressure is up. Good little example there. Okay? A person is sandwiched between two beds of nails and has a cement block placed on the upper bed. The cement block is broken with a sledgehammer. You guys have all seen this, right? The circus acts or carnival acts there, a person lying on a bed of nails. And then they'll even take a cinder block, put it on the person's chest, and someone else will take a sledgehammer and whack and break it. And the whole audience is aghast. Oh, he didn't go through the nails. He's not impaled. He's not dead. Well, no. It's the force of the blow is distributed over, and see what happens is the person's body is spread out all over the nails. So there's no way this person is going to go down into the nails, all right, because his force is spread out all over. And the combined surface area of the nails results in a tolerable pressure that will not pierce the skin. If there's any questions, just shout out. I don't know, are you guys still even there? Okay, right. I'm just going to check here and make sure. Yeah, good. What else we got? Mechanical laws of matter. You exert a force of 25 newtons on the head of a thumbtack. You know, those little tacks there that you push into cork boards or on the wall or whatever. And I'm just going to try and put that over there. In order to put a poster on the wall. The head of the thumbtack has a radius of 5 millimeters. What is the pressure on your thumb? Okay. So, here you'll have to go back into old time there. I think I put it on the formula sheet. You'll need the area of a circle. All right. And here I've given you the radius of the circle head of the thumbtack. So, if I give you the radius, you sub it into your formula there for a circle. Area is equal to pi r squared. And that's your area there that goes under here. And then you just solve and away you go. Okay? That's how this one goes. Pressure is equal to force divided by area. These are good kind of little comprehension questions here. A book sitting upright on a table exerts more pressure on the table than an identical book laying flat. So a book sitting up like this is going to apply more pressure than a book sitting like this. Why? Because the area is bigger than this one. Or sorry, the area for this one is much bigger than the area touching here. Okay? And number 2. A person with a weight of 60 newtons stands on the floor. The area of each shoe that is in contact with the floor is 0.1 meters squared. What is the pressure exerted on the floor by each foot? Assume equal distribution of weight. Well, here we go. A person with a weight of 60 newtons. So the person weighs 60 newtons, and we want to find out how much pressure is on each foot. Assume equal distribution, so that means each foot, in theory, is holding 30 newtons. I've given you the area of each foot, so there you go. Each foot is holding up 300 pascals. What would the pressure be if that person only stood on one foot? Well, there you go. 60 newtons divided by 0.1, double the pressure. Okay. What would be the pressure if the person balanced on the heel of one foot that had an area of here? So here you would find your area of your heel, sub it in there, and you'll see there. So you just think I have we started, we got before the pandemic, you know what I mean? Everyone had all these plans. My little girl was into figure skating and ballet, and you just look at the amount of pressure that um, a ballerina exerts on their toes. You know what I mean? Their toes are are straight up in the air. Incredible amount of pressure. Insane, actually. Couldn't even try it. Moving on. We're about halfway through, so we're kind of right on track. Pressure is a relative quantity. So when you measure a pressure, you're measuring it relative to some other pressure. Okay? Now, what does that mean? You know, you look at your tire pressure. It's different than air pressure. You look at the pressure there in your lungs. Um, you'll know there by your biology. I think you guys are maybe this week there. You guys are doing respiration. If it is, it's like one of the best units. And you'll see there that your lungs are always off kilter according to atmospheric pressure. And like what's called a pneumothorax is where you get a punctured lung, a deflated lung. You know, you hear about someone getting a fence post through their lung and they have a collapsed lung. It's called a pneumothorax. It's where the lung is the same pressure as the outside, it just deflates, right? Your lung always has to be a little out of sync so that air can move in, air can move out. Okay, so when when you measure your tire pressure, you are measuring the pressure in the tire. Okay, it's greater than atmospheric pressure inside the tire. Okay, so that's what we mean when we're measuring pressure. So what do we got here? We I don't really like using imperial or American British units of measure like feet and yards and all that. But there is one there that they still use. Okay, and it's pounds per square inch. Okay, 1 atmosphere. Okay, which is standard atmospheric pressure. You remember there from chemistry, 1 atmosphere is equal to 101.3 kPa. Okay, which is also equal to 760 millimeters of mercury or torr. Well, there's another one to add, and that's PSI. Okay, and 1 atmosphere, 101.3 kPa, 760 millimeters torr is equal to 14 PSI, 14 pounds per square inch. Okay, so let's have a look at this question here. What would happen if we drove a car into a room where the air pressure inside the room is increased from 14 pounds per square inch to 44 pounds per square inch? So here, I'm outside, I'm at a park, I have my car, it's 1 atmospheric pressure outside. My tires are more so, okay? They're 44 pounds per square inch. So that's why the tires are inflated, right? Because the pressure inside the tire is greater than it is outside. So the atoms are holding the tire up inside, okay, the tire. But then I drive into a pressure chamber where it is now not 1 atmosphere, 101.3 kPa. It is now 3.14 atmospheres. So the pressure is greater when I walk into this chamber. And what happens is the pressure that is in this chamber will now be stronger than the pressure inside of the tire. Because remember before, the pressure inside the tire was greater than it was atmospherically. But now atmospheric pressure inside the chamber is greater than the tire. So the pressure inside the tire would go to 0. And the tires would deflate. Kind of a weird question. But if you can get that to work, this question will really help you out as far as understanding how air pressure works. And if you ask me a question now or later or anytime, and we'll get that fixed. You guys remember this there from chemistry, Boyle's law. Okay, since gases are compressible, the volume of the gas can be changed as well. Okay, and if temperature is kept the same, there is a relationship between the pressure and the volume. And basically how I want you to think about this is scenario 1, scenario 2. And here I have a balloon at a certain pressure and volume. And then I have the same balloon. I've changed the pressure or I changed the volume and things have happened. And there's a relationship between these two. P1V2 is equal to, P1V1 is equal to P2V2. I'll update that there on the PowerPoint. Okay. So that's how that one works. Any issues with that? I think you guys should be good from that there from your previous 7 weeks there of chemistry. And you'll see here the relationship between pressure and volume of a gas. Lower pressure, okay, what's going on here? It's kind of the same thing, is if you, how do I say this here? You have a balloon. You have a certain amount of molecules in this volume. Everyone seems to be happy. But what happens if I decrease the volume? Decrease the volume. What's happening to the atoms in there? They're becoming, it's kind of the same thing as if you had 20 people in your living room and everyone's having an hors d'oeuvre and everyone's talking, but then you said, all right, everybody into the bathroom, let's go. And you couldn't, you know what I mean? Everyone's going to be uncomfortable. The pressure's going to be up. So when you decrease the volume, you increase the pressure. Or if you increase the volume, you're going to decrease the pressure. This works inversely. And you'll see here, under a high pressure system, you've got all these atoms. And pressure is just about collisions, atoms colliding. That's all it is, atoms coming into contact with each other. So if you have a big balloon, okay, with a small amount of atoms in it, your pressure is going to be really low. But if you increase the pressure there, your volume should drop. And you'll see what's going on here, okay? So low pressure, low amount of collisions. High pressure, high amount of collisions. Now we're going to get into a little bit of fluid stuff. And, you know, we could do a PhD on this. Again, we're just going to be kind of skimming the surface there to give you guys a general understanding. But 2 general properties of pressure in fluid. Fluid pressure acts in all directions. So when you try to push down on an inflated beach ball and you try and push it under the water, you can feel the water pushing back against the ball, right? You have a beach ball and you're trying to push it underneath the water at the beach. You're trying. The water is actually pushing back and saying, no, 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 you're not doing it. Right? And then maybe you do get the beach ball under the water and then you let go and then comes right back up. The water's pushing it back. Okay? And you can feel the water pushing back against the ball towards the surface. The force is due to liquid pressure acting against the surface to combine and produce a net force that acts perpendicular to the surface. What does all that mean? It's just pushing back against you. That's all it is. And the force of gravity causes the pressure in a fluid to vary with depth only. What does that mean? Like air pressure. Air pressure, let's say I have a pot of water. Water boils at 100 degrees Celsius. Why? Because here on land, and I mean land by the ocean, because that's, you know, as low down as possible. And if you look straight up, well, you've got 20 kilometers of air pushing down on you. And that exerts a force, an air pressure. Okay? And that is the reason why water boils at 100 degrees, because you have maximum amount of air pushing on that water and you're adding heat to it, and the water is trying to escape, but what happens is the air pressure is pushing that water down. So you have to get to 100 degrees Celsius in order to break so that the water can change into steam. All right. But if you take that same pot of water to the top of Mount Everest, now you only have 12 kilometers of air pushing down on that pot of water. So therefore now that pot of water will boil at 70. I think it's 71 degrees. And yeah, water on the top of Mount Everest boils at around 70 degrees because of there's less air pressure. Okay. And so even when you go to, you swim in the ocean, okay, that's why if you instantaneously went to the bottom of the ocean, the Marina Trench, what is that? 8 kilometers down? I don't know. It's just, it's so far down. All right. So now let's say you have 8 kilometers of water, not air, water on top of you. You would change into the size of a Coke can. And you'll see there that there's really not a lot, there's very few vertebrates, animals there with skeletons, spinal columns there, that you'll find at that depth. Generally, it's just kind of jellyfish and creatures there that can be supported by water. All right. So it does play the force there of what's going on above you will increase the pressure. How does the pressure exerted by a liquid change with depth in the liquid? How does the pressure exerted by a liquid change as the density of the liquid increases? In both cases there, the pressure will increase. So the more liquid that's on top of you, the more pressure. That's how it works. Discounting the pressure of the atmosphere, if you swim twice as deep in the water, how much more water pressure is exerted on your ears? If you swim in salt water, will the pressure be greater or less than in fresh water at the same depth? Interesting. Twice the depth, twice the pressure. And I think we showed that. I'm just going back here. Is this it here? Yes. You remember the pressure on 1 foot? 300 pascals. And so if I transfer my entire body weight onto, sorry, this was for 2 feet, right? 300 and 300. And if I transfer all of my body weight onto 1 foot, the pressure is doubled. Okay, so it works kind of the same way. What else we got? In salt water, the pressure will be slightly greater because salt water has a higher density. So salt water actually weighs more than fresh water. And if something is weighing more on you, you're going to have increased pressure. How does water pressure 1 meter below the surface in a small pool compare to the water pressure 1 meter deep in a large lake? Fresh water, they should be the same. Okay. Now we're going to get into we're going to move on to some interesting aspects there with fluid mechanics. Buoyancy. And it's we're going to get into how a ship the size of Titanic, which I actually just watched again there in the weekend, it's still pretty good. But it's the whole reason why a ship like Titanic can float. The thing weighs thousands of tons. Enormous. But how is this thing able to float? And you'll see there that it's kind of interesting. Buoyancy is the apparent loss of weight of a submerged object. So basically what we're talking about here is, remember, an object will never lose mass, but your weight can change, right? Your weight on the moon, weight on Earth, or your weight in the water. All right? Because the water, remember the beach ball? It's going to push back. So therefore now, your weight is going to change. It is easier to lift a heavy object under the water because of buoyancy. When you lift this object above the surface of the water, it is much heavier. So let's say you have, I don't know, a 10-pound weight, and you have it in the water, and it's in the water, and you're it's not that bad. Even me, I'm 100 kilos. I'm in the water. I can bounce in the swimming pool, right? Because the water is supporting me. You look at all the big dinosaurs, or like even a hippopotamus. What is the plural for a hippopotamus? Hippopotami? Hippopotamuses? I don't know. Anybody figure that out? Let me know. But a hippopotamus hangs out in the water because the water supports it. You don't really see hippos running around the savannah. Short little legs, massive bodies. They tend to like to hang out in water because they're supported. We found that the force of gravity on a fluid causes the pressure to increase with depth. All right? So the more water that's on top of you, the more pressure you're going to feel. This produces something we call a buoyant force that exerts an upward force on an object placed in a fluid. So this buoyant force, you're trying to push the beach ball into the water, while the buoyant force is pushing back on it. Okay? And you have a look here, just kind of an example. And just to let you know that you'll remember there from chemistry, the definition of a solution. Okay? Remember that a gas is also a solution. Like you look at air, okay? Has nitrogen, oxygen, all these different things, but the nitrogen is the solvent, and oxygen and carbon dioxide and all the other gases there, they are solutes. So the air acts like a solution as well. And the buoyant force is an upward force exerted by a fluid on a substance. Okay? Partly or completely immersed in the fluid. So you have a look here. Here you have a stone, or I don't know, a silly putty, quite frankly, I have no idea what this is. Let's call it a stone. And you put the stone in the water is going to push back on the stone. Hey, but then the weight of the stone is too strong, okay, and overcomes and just goes right down to the bottom. You'll notice there its surface area tends to have we'll get into that. Here I have a block of wood. Let's call it a block of wood because it's floating. Bricks, I assume, probably wouldn't float. And here, this thing is floating on the water. That means its weight, okay, cannot overcome the buoyant force, so it's just sitting there. Maybe it has a weight of 0. Interesting. And here we have a balloon. There is a mass of the balloon. There is a weight of the balloon pushing down. And then we have our buoyant force of the air. And when that balloon flies off, you can clearly state that the buoyant force is stronger than the weight of the balloon. And this is where we get into Archimedes' principle, which states that the buoyant force acting on an object in a fluid at rest is equal to the weight of the fluid displaced by the object. What does that mean? We'll get there. Very next slide. And the buoyant force is equal to the weight of the displaced fluid. This means the object will sink until the weight of the object equals the weight of the fluid displaced by the object. Okay, enough. Let's get to a picture. So here I have, I lower this into a container of water, and you see whatever this is, let's call it a brick, whatever, okay? And just hanging out in the air, it has a force of 10 newtons. It has a weight of 10 newtons, okay? And then I have a pot of water here with a little spout and a cup with another weight, okay? So I put this block into the water, and I get a new reading of 6 newtons. So the scale reading is reduced by the amount of the buoyant force. So I put this in here, and then the block is floating because now the buoyant force is pushing up against the block, and now I only get a weight of 6 newtons. Well, hey, wait a second. Where did the other 4 newtons go? Well, you see, you put the block in. Look at my volume right here of my water. And I put the block in there, and you see my volume changed because the block is pushing water out of the way so it can get in there. Well, the amount of water that came out, funny enough, is equal to 4 newtons. So you still have your 10 newtons of force here. So this is Archimedes' principle in a nutshell. So basically what's this said right here is demonstrated by here. Here I have a weight of 10 newtons. I put it into the water. Now it registers as 6 newtons because of the buoyant force. Well, what happened here? Well, it pushed out 4 newtons worth of water. So everything is added and accounted for. Okay. Principles of flotation. Why do some objects sink while other large objects float? And the key here, like we're all getting into now, this is the how does the Titanic float? And the key here is density. If the density of the object is greater than the density of the fluid, the object's weight is greater than the buoyant force and the object sinks. Read that again. If the density of the object is greater than the density of the fluid, the object's weight is greater than the buoyant force and the object sinks. So the density of the object, density of the water, if this one is more dense, it's going to sink. All right? And we can use that same analogy for right here. Here I have a stone, all right? Much more dense than this, than the buoyant force of the water, so therefore it goes right there, goes right down. If its density is less than the fluid, it floats. That's why the block of wood, or that's why ice floats in water. Because water is actually very dense, but then when it freezes, all those water molecules space out and hook up in some crystalline structure, right? Like ice, snow. And you'll see there that this is liquid water, all like this. The atoms are like this, but ice, the atoms are like this. So ice is actually less dense than liquid water. That's why a 1,000,000-ton iceberg can float. 1,000,000-ton. Here we got. A 1-ton block of iron will sink when placed into water. Of course it will. This is because iron is very dense and will not displace water to prevent it from sinking. The weight of the iron block is greater than the buoyant force and therefore it sinks. Okay? What if we reshape the 1-ton block of iron into a big salad bowl? All right, so we had a 1-ton block of iron like this. We put this there into water, right down to the bottom of the swimming pool. But now we have reshaped the 1-ton block of iron into a great big salad bowl. What happens here? It will displace a greater volume of water than before. The deeper the bowl settles into the water, the greater amount of water that it displaces. The more water displaced, the greater the buoyant force. So you see, the more water, and you see, you had a block of iron, and it went right down to the bottom of the pool because it didn't really push out any water, right? It's this big. You didn't push out any water, it just went straight down. But if we shaped it into a big salad bowl, look how much surface area I have now touching the water. Still 1 ton, still pushing, but because now I have more contact with the water, my buoyant force becomes strong, Okay, the more water displaced, the greater the buoyant force acting on it. And when the buoyant force equals 1 ton, it will sink no more. Okay, so a floating object displaces a weight of fluid equal to its own weight. So you see here, just look at this thing. This, I don't know, a million tons, 100,000 tons, I don't even know. Just ridiculous amount of weight on water. And you see what they're doing is they've increased the surface area so much that now it's pushing all this water away because of all the surface area. And now the buoyant force is pushing back on it, and it's able to hold all of this. Same is true for objects in the air. Remember that air is a gas, and a gas is a fluid. Archimedes' principle applies to objects in the air just like it does in the water. An object surrounded by air is buoyed up by a force equal to the weight of the air displaced. It's the same thing. This the Goodyear blimp here, it's to be up in the atmosphere, it's pushing air out of the way. And look at that surface area. So if it's pushing this air out of the way, the air is pushing back, and that's how this thing is able to stay in the air. The volume of a submerged object is equal to the volume of the fluid displaced. I like these. You can see here that they're for this particular unit, and which is why I wanted you guys here. I didn't want to do this as a kind of a dead recording. I wanted you guys here because you can see here that there are some math questions. Math questions aren't that bad, but there's a lot more of understanding comprehension. Okay, so I kind of like these. The volume of a submerged object is equal to the volume of the fluid dispersed. The weight of a floating body is equal to the weight of the fluid dispersed. Kind of makes sense, right? It all goes back to this one. Right there. That's it in a nutshell. Great slide, by the way. Made it myself. Number 3, why is it easier to float in salt water than in fresh water? Salt water is dense, more dense, okay, and therefore it'll have a greater buoyant force. And when I was traveling there, I didn't have a chance to, I tried, just didn't work out for me, to go to, I made it to Jordan in the Middle East there, and I saw Petra, and but I actually got food poisoning there from Cairo, so I was stuck in my hotel room for 6 days out of a 7-day holiday. But I didn't make it to the Dead Sea. But the Dead Sea is the lowest point on Earth, and it's a little sea there in the Middle East that is so saline, so salty, that not only do you not have to, you're swimming in a swimming pool, if you don't keep your arms moving, you'll sink, right? But in the Dead Sea there, you'd sit right on top of the water because it's so salty, all right? It has such a huge buoyant force. What is Archimedes' principle? Go for it. Number 5, how does a buoyant force on a fully submerged object compare with the weight of water displaced? They will equal. Okay. Does the buoyant force on a fully submerged object depend on the weight of the object or the weight of the water it displaces? Only on the weight of the water. Okay. That's how the buoyant force works. The weight of the water it displaces. What is the buoyant force that acts on a 100-ton ship that is floating? Good question. Have a look at this one. Let's understand this one. What is the buoyant force that acts on a 100-ton ship that is floating? Since it is floating, the buoyant force must be at least equal to the weight of the fluid it displaces. Therefore, the force must be at least equal to 100 tons of water. Okay, good question. A balloon that weighs 1 Newton is suspended in air, drifting neither up or down. How much buoyant force acts on it and what happens if the buoyant force increases or decreases. So it's tied up, and because it is neither going up or down, then we know that the buoyant force and the weight of the balloon are equal. Therefore, the buoyant force, when it's tied up, is 1 Newton. All right, what happens if the buoyant force increases? If the buoyant force increases, the balloon will go up. If the buoyant force decreases, the balloon will come down. Okay. Pascal's principle. Here's another one. Static fluids. So here, these are fluids that are not moving. All right. And the pressure applied to an enclosed fluid, is transmitted undiminished to all parts of the fluid and to all parts of the container. What does that mean? Have a look. And you see here I have this kind of crazy contraption here, and you'll see that I have this. It's all one system. So here I've got kind of a test tube kind of a thing. Here I've got this swirly CSI thing. Here I've got this one here with 2 bulbs, and here I have just a straight smaller little test tube section. And interesting, you have a look at what's going on here. The pressure applied to an enclosed fluid is transmitted undiminished to all parts of the fluid and the walls of the container. So the pressure is the same everywhere. It doesn't matter the shape of the container. So example, if the pressure of the city's water is increased at the pumping station by 10 units of pressure, the pressure everywhere in the pipes will be increased 10 units. So at the water tower there, north end of Barrie by the Georgia Mall, if they increase the pressure by 10 units there, everywhere, every single faucet in Barrie that water tower is hooked up to will be increased by 10. That's just physics. Okay? And you have a look here. This is how your brakes work. And I've got a couple slides here that I will show you, okay? The piston on which the force is applied, okay? Like you press the brake, and that induces a pressure right here, okay? And then that pressure, you see you're pushing down on this fluid, brake fluid, inside your pedal, and it's pushing down, increasing the pressure. And you'll see there that the piston that applies the force has a larger area. And you see what's going on here? We can actually change things around to suit our needs. See here, the piston on which the force is applied, your pedal, is just little. But then, using the same, we can actually increase this. So let's have a look here. Since the pressures are the same, the output force is. So here, you remember, pressure is equal to force divided by area. Well, here I've got my input and my output. They have to be the same. But now I can now you have a ratio here. Okay? Force input divided by area input is equal to the force output divided by the area output. So now you have 4 bananas here. Look, you can solve for one of them. Okay? And I'll check the formula sheet. I think it's in there. Okay? And you can flip this around, and now you can solve for one. So if I gave you this one, and this one, you can solve for F input. I could ask you, what was the area of the input? So you flip this around and you solve for this. With the output piston's area larger than the input piston's area, the output force is larger, okay, than the input force. So we can actually increase the force. You have a look here. The force applied on a small area, okay, well, it's coming along here. We increase the area here, and we have the output force, which is larger. And you have a look. The questions there that I posted, they deal with this directly. And I really, really, really recommend that you guys have a look at the questions there. They're not that bad. Like, honestly, you could probably do them in 25, 30 minutes. And it's actually good to know about braking system, and it's actually, you'll have to know this there for test 3. So it's a good thing anyway. A common example is the braking system in your car. And you have a look here. Here's your brake pedal. Push down on it. Here's your master cylinder. Okay. Your brake fluid. Okay. And what happens is you push down on this. That applies pressure to here. And you see, look at the area here of your brake pedal. And then look at the area here. Your wheel cylinder. And then this pushes there on the brake pad, which then right onto your stops your wheels there from moving. And you have a look at what's going on. I'm sorry. Hey, what's going on here? There we go. Okay, so this is how your brakes work, and yeah, we'll just have a look. So these are for static fluids. Sorry, I forgot to say. Pascal's principle here is for static fluids. You see these fluids, they're not moving. Okay, you're applying a pressure to them, and we can augment the output force there. Okay, just by changing the surface area of what's going on. Okay, but these fluids are not moving. Quickly, there is Bernoulli's principle, and this has to deal with moving fluids. And I'm gonna read this, but it so far we've spoken only of static fluids. Okay, that was Pascal's. But what about moving fluids? And when the speed of a fluid increases, the pressure of the fluid decreases. So just have a look here. Here I've got kind of a wide cylinder, okay, and this fluid here is moving. This is a pipe, and you'll see here that in this area here, okay, here we've got slower moving water because it's able to handle the volume. But then you see we've got to get the water through this small little area right here. You can see there that we're going to have different amounts of pressure. Slow moving, high pressure. Fast moving, low pressure. Again, write that down. Slow moving, high pressure. Fast moving, low pressure. And like if you look at like a nice sunny day is 101.3 kilopascals, 1 atmosphere, right? On a nice sunny day, no wind, we have good high pressure. On a cold, rainy day, or like a hurricane, very fast moving air, windy days, you'll see there that hurricanes have a low pressure. You'll hear in the weather network there that, there's a high pressure system moving into the area. High pressure means sunny days, no wind. Oh, there's a low pressure moving into the area. Oh, low pressure means rainy, windy, cold, fast moving. So, and you'll see here that here's a good little movie. Please have a watch of this movie. I can't show it there for copyright, but it's a really, really good little movie. Talks about these two, laminar and turbulent. Bernoulli's principle applies to laminar steady state flow. Okay, this turbulent flow leads to a decrease in kinetic energy. You'll see here that all the water is kind of moving in a uniform fashion, easy peasy. But when you get turbulence, now you've got water or the air is all just hitting the sides of the container and moving all around. It's just mashed potatoes. That's what we call turbulence. I wanted to show you guys this, and I hope there that it works. We'll see here. This is an airplane, kind of the side of an airplane. All right. and the airplane is moving this direction. And so the wind is moving back. And here I have a double wing. All right, this is the first plane in history that has 4 wings. All right, good enough. But I just want to show you there that a 50-ton airplane is up in the air just because of air pressure. And it's the same thing as what's going on here. Here I have a piece of paper, and I'm going to blow on top of it. And you think, if I blow on top of a piece of paper, shouldn't it go down? But you see, the air pressure in this state, the air pressure underneath is the same as the air pressure on top. Sorry, I'm just going to turn this off. Or break it. Good enough. Okay, so going back to this. Here we have the air pressure is the same on the bottom as it is on the top. But if I speed the air up on top, that's a pretty heavy piece of paper. Let's try this one. And you'll see there that the fast moving air on top of the paper is low pressure now. I still have the same air pressure underneath, and that's what pushes it up. And it's the same principle there what goes on for an airplane wing. Airplane wings are designed for this purpose only. As the plane is moving forward, the wind is coming back at the plane, right? And what happens at this point in time is the air separates. It gets cut in half by the wing. And half the air goes under the wing in a straight line. The other half of the air goes on top of the wing. Now, it's got a longer distance to travel than this air. So it's got to move it faster than this air because it has to meet this air at the same time as it comes under the wing. So this air has got to move faster to get to the same spot here. So on top, we have fast moving air. On top, we have lower pressure. And here we have the same pressure underneath. And that's how a 50-ton airplane gets lifted. By exactly the same pressure as I lifted this piece of paper up. Okay. Other examples of Bernoulli's principle, a curveball and a baseball. Okay. Cars and trucks passing on the highway are drawn together. You'll notice that there's kind of this, almost like a suction. And umbrellas are inverted on a windy day. All right. Test yourself. Blimps, airplanes, and rockets operate under 3 different principles, which operates by buoyancy, by Bernoulli's principle, by Newton's third law. Blimps, airplanes, and rockets. Blimps, buoyancy. Airplanes, Bernoulli's. Rockets. Every action has an opposite and equal reaction. The fire comes out at the back end of a rocket. Well, choom, that thing is going to the moon. And thank you guys so much. I won't keep you. I apologize. That was a bit longer than I anticipated, but I'll post this there to YouTube. Tomorrow, week 8, we're on to temperature and thermodynamics. It's not bad. It's MC delta T. Sorry, Q is equal to MC delta T. You guys did that there in chem. There's, I think, 1 or 2 new formulas, but nothing's too bad. Get out of here. Enjoy your day. Stick around if you have a question. Other than that, take it easy, guys, and we'll see y'all tomorrow. I'm going to stop recording now. No, it's all good. Thank you, Mallory. You have a great day, too. And